say here at this point, for example, we're interested in knowing the distribution of the stress about the point. So pretty much just like your homework, and you might be able to analyze the reactions, and then from there you can calculate locally the distribution of the normal stress and machine stress. And after the ending of your calculation, then probably you can try to draw a small cube like this. And again, here we assume the whole whiteboard is an elastic object. So locally around this point, and after you proceed all the calculations, then you can draw the small cube. And then on that cube, you might be able to align the coordinate system you have defined. For example, here is x direction, here is y direction, here is z direction. On this cube, you'll be able to, from your calculations, you can impose around the point here. For example, here will be the normal stress in sigma x direction, and in balance, so the back will be the same value. And in general, you might have the stress in sigma y direction on the back in balance, and then in the z direction, normal stress z. Okay, so that is based upon the result of the combined loading. And furthermore, you might have the shrink stress. And for example, the shrink stress on the x-plane will be this one is called the x-plane, and this one has a normal to y called the y-plane, z-plane. So the shrink stress on each plane would have this direction, tau xy on the plane, and pointing to z direction, this is tau xz. And this one is in the z plane, pointing to x direction, so this is tau zx, and etc. So let me make one more. For example, on the y plane, or how about this, on the x plane, pointing to y direction, so this is xy. So in total, we should expect the 9 stress components. So in general, there are stress components. And for the normal stress, sigma x, sigma y, sigma z. And for string stress, and here is tau xy, tau xz. So that both are on the x-plane. Just like we draw here, the two components are here. And on the y-plane, we have yx and yz. And on the z-plane, we have zx and zy.
For one of the green ones, which one is x? Which one is tau yz?
Which one tau yz?
Yeah, you labeled, isn't it the
Yz is in the y plane, pointing to z direction. This is a tau yz. Are we okay?
Is your zx wrong?
Zx wrong. So this is in.
that? Yeah, is that one?
So this is in the z plane, pointing to x direction. So zx. For tau, for example, xy, the first symbol indicate which plane is on, and this one indicate which direction is pointing to. So this is xz, this is tau xz, right? This one? Okay?
Okay.
And then this one is in the z plane. On the z plane pointing to x direction, so this is tau zx. Okay? Okay, so in total we have 9 stress components in general. Yes?
I'm having some trouble. So tau xz, is that on the face of the board, the face of the object that's theoretically closest to us, you can say.
Isn't that tau YZ for the one facing?
Yeah.
Let me do this one more time. Let me draw that bigger one, okay? So X, Y, and Z. And now here I only label the shear. So right now we label on this plane. So that is the tau X pointing to Z. So that's a tau XY. And here is tau XZ. Okay, so now we label on the top. And here is in Z plane, pointing to X direction. This one is in Z plane, pointing to Y direction. Okay, and now we label the Y plane here. So that is in the Y plane, pointing to X direction, and in the Y plane, pointing to Z direction. Okay, so basically using these conventions. And here,
You labeled your tau XY.
Yeah, that's.
tau XY is this one.
Which base is tau XZ on?
Which base is tau XZ on?
Because it's not on the X,
Tau XZ is on this plane,
on the face. Okay.
on the face, on this face.
And XY is on the bottom.
XY is, again, the XY is still on the face, on the same face.
Okay.
Yeah, the two green shearing is on the same face. Okay. And the same thing, the two red shearing is on the Y face, and the both blue on the Z face. So in total, we have 9 stress components, and those are called the 3D stress. So that means the distribution of the stress in 3-dimensional. And this is the most general the case for the distribution of the stress. And to analyze the 3D stress is we need additional tools. And so the learning of the chapter 7 is try to learn the basic principle. So that means we try to learn the simple case, which means 2D stress. Okay, so that would be easier. So now I want to give you the definition of the 2D. So for the 2D stress, we might be able to take one is this. One scenario is this. The 2D stress would be have, say, the OD stress component. Pointing to Z direction R0. This is one scenario. The other scenario is all the stress component pointing to Y directions R0. The third scenario is all the stress component pointing to X directions R0. Nothing more, nothing less. For the 2D stress, we only have 3 scenarios we can talk about. Okay, and loading scenario will be based upon the loading. We can apply the loading to achieve either of the those kind of 3 scenarios. And I can give you one example is this. So for example, if you would think this is a very thin, this actually is a three-dimensional object, but you can see these, there's a three dimensions: length, width, and depth. In the third dimension, the depth is very small compared to the other two dimensions. So for this one, this object, sometimes we can call it as a membrane. The membrane, that means it's very thin in one dimension. And now if you would imagine this is a membrane, and then if I were able to apply loading in two dimensions, in this and also in this simultaneously. Okay, so in this way, for this object, we can tell in theory, they shouldn't have any stress in this direction. All the stresses will be in plane. Okay, so like you blow your chewing gums, you blow it, okay, and then eventually it's going to blow up because the chewing gum's material properties won't be able to hold the pressure you keep pushing in. So the surface tension will be eventually less than the pressure inside, so the bubble blows up. For that case, that is the bubble surface is another membrane examples. So for that case, you shouldn't expect any inside the membrane, inside the bubbles, the chewing gums, you shouldn't expect any Z direction stress. Okay, so that's one example. So by using certain systems, certain object, and using an appropriate loading case, we might be able to achieve either of one. So for those simple cases, then we can simplify the complicated three-dimensional into 2D. And then for these illustrations, let me demonstrate what is this case using our diagram here. So for this diagram, you can see all the stress component pointing to Z will be equal to 0. So that means this will be equal to 0, again for two-dimensional stress components. And then with pointing to Z will be equal to 0, this will be equal to 0, and then this will be equal to 0. Okay. And for this case, then we can try to draw the loading scenarios. So for this one, let me put into three-dimensional cube again to see what happens. So this is the x directions.
Excuse me.
This is what? Yes.
So why is the shear stress from Z x 0? Because that's not necessarily pointing in the direction of
yes.
Z. That.
Let me leave it that one at this moment. Okay, let me leave it. I can explain now. So in our chapter 1, you have learned, for example, if this is the x, if this will be Z direction. So this will be, this one will be tau in the x plane, pointing to Z direction. So this is tau xz, okay? And now for our scenario 2D, this is equal to 0. And from chapter 1, we know that once on one side we have the shear stress like this, the other three sides will be like this. And they must have the same value, which is equal to 0. And what is this component? This is in the Z plane, pointing to x direction. So this one is equal to 0.
Okay.
Okay, so that means here, I think that's a good question because originally I like to reserve until there, but since you asked, so in this way, this will be, in magnitude, this will be equal to this, so that's equal to 0. In magnitude, this one will be equal to this one.
So that one's also 0.
So that will be equal to 0.
Okay.
Okay? So now we have how many? 1, 2, 3, 4. Only 4 stress components, and then let me draw that one here. So for the 4th stress component, we have tau sigma x. So sigma x is in normal to this x plane. And here on the back, and sigma y, and on the back, sigma y. Those are the normal stress, normal to the surface. And then we fix this, tau xy. What is tau xy? tau xy is the, on this plane, this is the x plane, and we have tau xy. So tau xy is on the x plane, pointing to y direction. So this is tau xy. And then we have tau yx. Tau yx, that means on the y plane pointing to x direction. So this is y plane. On y plane pointing to x direction, so this is tau yx. And there's another 2 on the back side of the surface. So that is a 2D, and this is a 2D stress component, and that is one simple scenario that can be simplified from the 3D. And in general, in terms of the drawing, we can even simplify our drawing of this cube. And for this cube, we call it stress element or stress cube. Either way, whatever the name you do it. So even we can simplify the drawing by this. If you would think you are the small person, you're sitting on the z-axis looking downward. Okay, what you see will be like this. In front of you, we see is a square. It's a square stress element. On that stress square element you are looking at is in x, y directions only. In the x direction, you have the normal stress sigma x. In the y direction, you have the normal stress sigma y. And also in front of you, then you will see the strain stress tau xy, and this is tau yx, and the same thing on the other two sides. This is a tau yx, so this is tau xy, right? Okay, so that is a one. If you have textbook with you, that is the symbols you see. You will see from the page 1, pretty much page 1 of this chapter to the end of this chapter. So this is called the two-dimensional stress element, and which is used to describe the 2D stress conditions. In these chapters, we only study this case most of the time. Okay, so that is our starting point. And from here, you can see this one is a simple case corresponding to this scenario. That is one simple scenario of the most general one. Okay, so any questions about where we're going to start? We're going to start from here. Okay. So now based upon our two-dimensional stress scenario, and then again, we're back to our original thinking. Again, here we think the whole whiteboard as an elastic object. And now here is a point. For example, at this point, we know, for example, we presume that this question is 2D stress and the 2D stress problems. So around this point, we can draw a stress element. So this is called a stress element. Stress element is a square locally that has the very small dimensions. Try to describe locally the distribution of the stress around one point. Okay, so let me copy that one, and then depends on the coordinate systems. For example, if you like to define your coordinate system xy like this, it's okay. If you like to define your coordinate systems like xy, always use right-hand rule. It's okay. As long as you have your coordinate systems being defined, you stick with your symbols. Okay, so here, for example, this is xy. So here is sigma x. Let me repeat. Sigma y. And here is tau yx. This is tau xy. And tau yx. And tau yx, tau xy. Okay, so in here, for static equilibrium, we have to ask the magnitude of tau xy equal to the magnitude of tau yx. Okay, so which means the strain stress, both the two components in magnitude, they must be equal. I mean, the 1, 2, 3, 4 strain stress components in magnitude must be equal, but they are different quantities. Okay, so here is our starting point. And now we come to the question is this. Right now you can see, again, this stress element is I chose is to draw is in this right